Welcome to the training module titled Comparing NWP Simulated Satellite Imagery to Observed Satellite Imagery. We'll also refer to the simulated imagery as synthetic imagery, so we'll hear both terms in this training session. My name is Dan Bicus. For our learning objectives, we'll look to understand the generation, display, and limitations of the synthetic/simulated imagery. We'll also introduce how the use of synthetic/simulated satellite imagery from NWP can aid in the forecast process of cloud cover, low cloud and fog, convection, as well as extratropical cyclogenesis. Finally, we'll look at how to verify synthetic/simulated satellite imagery with GOES-R imagery. Throughout this module, we'll be looking at the synthetic imagery from two different models, the Nissel-Whorf ARW model and the NAM-NEST, both at 4 km horizontal resolution with output from the 0Z run. Certain model output fields, including cloud water, cloud ice, temperature, water vapor, and so forth, are used as inputs to a model that generates the synthetic imagery. The radiative transfer model uses inputs from those model fields and outputs brightness temperatures at a number of spectral bands. For more detailed information, refer to this article. Synthetic simulated satellite imagery is becoming more popular. We expect this to eventually become a standard model output field, much the way simulated radar reflectivity has become. For that reason, be aware of which model you're analyzing. The forecast output availability will vary by model. For example, from the Nissel-Whorf, it's available hourly for the 9 to 36 hour forecast, valid 9Z of day 1 to 12Z of day 2. And for the NAM-NEST, it's hourly for the 0 to 36 hour forecast, valid 0Z of day 1 to 12Z of day 2, but then 3 hourly after that for the 39 to 60 hour forecast, so it does go out further in time. Another reason you want to be aware of which model you're looking at when you're looking at the synthetic or simulated imagery is that the microphysics package has a large influence on the appearance of simulated clouds. For details about this, refer to the article, but in the next slide we'll be looking at an example. Let's compare the IR imagery from the Nissel-Whorf ARW with the NAM-NEST, both at 4 km spatial resolution with the same color table. The bands are slightly different, but for all practical purposes are the same for this comparison. What is different between these is the microphysics packages. The Nissel-Whorf uses WSM6, while the NAM-NEST uses Farrier microphysics. The WSM6 microphysics package has a known bias to underestimate areal extent of convective clouds. That's with respect to GOES or the NAM-NEST synthetic imagery. Keep in mind, just because the Nissel-Whorf is underestimating areal extent of convective clouds, it doesn't necessarily make it a worse or better forecast than the NAM-NEST. Here's a synthetic 10.35 micron band from the Nissel-Whorf ARW model. This spans from the morning hours to the afternoon hours. Note that it shows an area of stratus across much of the central and southern plains. During the morning hours, it's forecast to dissipate by the afternoon, and with that we see some afternoon convection developing in this region. Here's the GOES 10.7 micron imagery, and you can see in agreement with the model output, much of the stratus that we saw across the plains has dissipated by midday, allowing for sufficient insulation and destabilization to take place for thunderstorm development from Nebraska down into Oklahoma. This is the synthetic low cloud and fog product from the Nissel-Whorf ARW model. This imagery is produced by subtracting the simulated brightness temperature at 3.9 microns from those at 10.35 microns. This appears similar to the GOES low cloud and fog product you may be used to analyzing. However, there are a couple key differences. First, due to computational limitations, nighttime is assumed constant in the calculation of the 3.9 micron imagery. Therefore, the brightness temperature difference remains positive even during the daytime, since there's no reflected solar radiation. Second, there's a false cloud signature in the southwest at certain times due to surface emissivities at these wavelengths. We can see a few of these in New Mexico, in Arizona, also out in this region as well.
You can identify these positive brightness temperature regions that are stationary for long periods and appear in generally the same places in the southwest U.S. Keep in mind that the simulated imagery does not discriminate between low cloud and fog. The GOES-R fog low stratus product is recommended to make that discrimination at analysis time. Note how easy it is to discriminate between forecast high and low cloud in this product. High clouds are these black, gray clouds, while low clouds are various shades of blue, like we see over the plains here, with increasing confidence of low cloud in the darker shades of blue, as we see in this color table. This color table choice is important for this product, therefore we advise this color table for analysis. This is the synthetic water vapor imagery at 6.95 microns from the missile wharf on the left, and then the corresponding 6.5 micron imagery from GOES on the right using identical color tables. This slight difference in wavelengths accounts for why brightness temperatures appear generally warmer with the synthetic imagery. When analyzing extratropical cyclones, focus on cyclogenesis components such as conveyor belts, jet streaks, and short waves that may contribute to intensification and so forth. In this particular example, we'll pretend like we're forecasting for the Boston CWA, and we're concerned about this dry slot that's moving in. So what you can do is analyze this before the event in the synthetic imagery. You can see our dry slot right here. How does it compare with the observed imagery on the right? Look at it for a later time, and we see its position. So the idea, if it seems to be doing pretty well in the forecast in terms of its timing and location, that would give you increased confidence for what you'll see at later times over here in the model forecast. For this case, we'll be analyzing the synthetic 10.35 micron imagery from the Missile Wharf ARW model. Let's pretend that we're forecasting for this region. You'll be assessing the clearing trends for potential thunderstorm development during the afternoon hours across the region of interest. This process entails identifying where morning clouds may exist and if and when they're forecast to dissipate, so that insulation may contribute to destabilization. I'll let you analyze this loop for a moment before moving on to the morning GOES imagery to assess your confidence in this forecast. Here's the verifying GOES visible imagery through 19Z. For the region of interest, assess your confidence in the model forecast. You may go back and forth between this slide and the previous if you need more time looking at the simulated IR imagery. Here's the verifying GOES visible imagery during the late afternoon and evening hours. Hopefully you caught on to the trend that low clouds were persisting in northeast Colorado, extending into western Nebraska, much longer than forecast by the wharf. The low clouds prevented destabilization and therefore thunderstorm development across that region where thunderstorms had been forecast. The model seemed to do a better job in central and southeastern Wyoming, where clearing and destabilization took place. The storm in southeast Wyoming was severe for a period of time before eventually moving towards the low clouds where it was weakened. This example illustrates how to compare the simulated imagery with the observed imagery throughout the day so that you may assess confidence in the model output in an efficient way. In conclusion, the synthetic simulated imagery allows one to see many processes in an integrated way compared to looking at numerous model fields and integrating them mentally. We looked at a number of applications including cloud cover, low cloud and fog. Remember, from the forecast perspective, you can utilize the synthetic simulated imagery, and for a diagnosis, use the GOES-R fog low stratus product. For convection, with the IR imagery, look for clearing trends for destabilization. With the water vapor bands, look at the jet streaks and short waves. You can also analyze elevated mixed layer, elevated cold fronts, and so forth. For extratropical cyclogenesis, remember to focus on cyclogenesis components such as conveyor belts, jet streaks, and short waves that contribute to intensification.